post the quiz on Canvas. So take a look for that today or tonight. It should be up. I have your exams. I'll hand those back near the end. All right, where did we leave off?
We were talking about systems.
System, okay. Here. All right, yeah, two types of systems. Two types of closed systems, I should say, in general. For systems, we use the closed system. You guys remember the definition of a closed system? Yeah. But energy can be exchanged. The closed system can be fixed volume or variable volume. That's fine. But the two types of closed system that I'm talking about, well, I guess we have fixed volume and variable volume, but we have more to it. And that's how I define the system. You know, we divide up the universe into the system and the surroundings here. And the system is going to be, you know, the object of interest or the reaction of interest here. And then everything else is the surroundings. So an object would be an example of that, like water, 50 grams of water. And the 50 grams of water can, if we add energy, it can heat up. Or if we remove energy, it can cool down. So this is energy here. And so if we look at the total energy change, delta E, which is the same thing as the total internal energy change, delta U, it's going to be the change in kinetic energy plus the change in potential energy. So when water absorbs energy, it's going to get warm, or if it loses energy, it's going to get cold, but it's still going to be water. If it's still water, the potential energy doesn't change, and the only thing that changes is the kinetic energy, which is the temperature here. Whereas when we're defining the system as a reaction, the reaction's a little bit different, because what we do is, like this reaction, methane plus oxygen yields CO2 and water. This is very exothermic. And so what's going to happen is, as this combusts, it's going to get very hot. And so the temperature is going to skyrocket, you know, closer to 1,000 degrees C. But it's not going to stay at 1,000 degrees C forever. What's going to happen is it's going to cool down. And so if we're looking at an exothermic reaction, you know, we want to see the total amount of heat that's released into the surroundings. And so if we want the total amount of heat released in the surroundings, we got to wait until this cools back down to 25 degrees C. So if we start off at room temperature, we're going to end up at room temperature. And then all the energy that this reaction can release to the surroundings, it will. And so for reactions, we have the initial temperature and the final temperature the same. If the initial temperature and the final temperature are the same, then what we see here is a situation like this, where we're looking at delta U, which is equal to delta EK plus delta PE. If the temperature doesn't change between the final and initial, the temperature can change in between the final and initial, but what we're looking at are state functions. Do you guys remember what a state function is? Like delta T is a state function, delta P is a state function, delta V is a state function, versus path-dependent functions. The state function only depends on the final state, 25 degrees, and the initial state, 25 degrees. It doesn't matter how it got there. So I don't need to know what the intermediate temperature here was. I just need to know the final and the initial temperature. And then when I look at the final and initial temperature, I see that the kinetic energies, the net change in kinetic energy is 0. Even though the kinetic energy skyrocketed, but what happened was it dropped back down. And so that there was no net change between the final and the initial state. Of course, the peak temperature there is going to depend on the path it takes, you know, what the surroundings are. The surroundings water or the surroundings something else. You know, depends on the path. But anyway, what we see here is delta EK is 0. So the only change here is in potential energy. So what we call this is chemical potential energy. So the chemical potential energy of methane and oxygen is different than the chemical potential energy of CO2 and water. Methane and oxygen is what we call an explosive or potentially explosive mixture, whereas CO2 and water doesn't risk explosion there normally, especially under conditions of constant pressure, which we'll work at. So there's a significant change in chemical potential energy. So when we look at the potential energy, we plot that as some arbitrary axis on the y here. And so we see that methane gas and O2 gas are at higher chemical potential. This is methane plus 2 O2s. And then CO2 gas and 2 H2O liquids. We have to balance this. And so this was a change in potential energy because the kinetic energy doesn't change since the temperature didn't change. Here. Now, when we're dealing with a closed system, you know, it could be constant volume or constant pressure. What is more common? Constant volume or constant pressure for us?
Pressure.
Constant pressure. If we're dealing with constant pressure, then we're looking at delta H. If we're dealing with constant volume, then we're looking at only delta U here. And so really what we're interested in is delta H, since we're dealing with mainly constant pressure systems here. And so when we look at delta H is equal to Q, which is the heat divided by the amount, or Q. These are two systems here. When we have the reaction, we use this. This is our reaction. When we have an object, we use this. Q is equal to MC delta T, or something similar to that. And so this is a reaction. This is a object.
What does that say, the reaction?
What?
What does that say, the reaction?
This one?
Yeah, what does it say in the circle?
Delta H is equal to Q divided by the amount. Or Q is equal to the amount times delta H. And so we have two different equations we use depending on if we're dealing with an object versus a reaction or process. Now, the difference between an object, one big difference between an object and reaction is object doesn't vanish. The object is there. So if we have 50 grams of water and it warms up, we still have 50 grams of water. However, if we have 50 grams of reactant mixture here, the reactants react, and once the reaction is complete, the reactants are gone. And so the reaction has a finite life. And so there's a finite life. After reaction, all that remains is surroundings. So the system's gone once the reaction's done. However, when we have an object, the object has like an infinite life. You know, the object is going to be around. So after it cools down, it's still there. So that's another key difference here. All right, so these are the two types of systems that we look at, and for closed systems, it could be constant volume or constant pressure. So for example, we could do this reaction here, the methane, under either constant volume conditions or constant pressure conditions. So it makes a difference in this particular case. Somebody mentioned delta N of gas or delta N of gas. Delta N of gas is important because when we look at this, I have 1, 2, 3 moles of gas on the reactant. Over on the product, I only have 1 mole of gas. Do you know the molar volume of a gas at room temperature and about 1 atmosphere of pressure? 22.4 is at 0 degrees and 1 atmosphere. If you warm that up to room temperature, so you go from 0 to room temperature, the gas expands a little bit. And so it's about 24.5 liters, or roughly 25 liters. And so if we say 25 liters, this is 3 moles of gas, that's 75 liters. And this is 1 mole of gas, that's only 25 liters. So we're losing about 50 liters of gas here. Liquid water, 2 moles of liquid water is 36 grams. 36 grams is only 36 milliliters. That's like 0.036 liters. And so this doesn't have much volume compared to the gases, kind of negligible volume. And so oftentimes the solids and liquids are ignored because the volumes are small compared to gases, and they use the simplifying assumption for that. But we may or may not, doesn't matter here, but we're losing about 50 liters. If we lose about 50 liters, if it's a constant volume, then the pressure is going to go way down. We have a risk of implosion. The opposite scenario is when we gain moles of gas, we're gaining volume, and then we have an explosion risk. A different type of explosion, though, a pressure explosion, versus an energy explosion like this. Well, anyway, most of our reactions are under constant pressure, and so we're primarily looking at delta H calculations for this. So you'll want to review all the ways of calculating delta H. Do you remember all the ways to calculate delta H? The enthalpy change. So I haven't talked about this yet, right? Second law, calculations. All right, started it. Okay. What's observed, this is the second law of thermodynamics. The second law of thermodynamics, actually, this is not the second law. This is delta S of the universe. I'll tell you the second law of thermodynamics. The second law of thermodynamics is this. Delta S of the universe is equal to delta S of our system plus delta S of our surroundings. And if this is greater than 0, then spontaneous. That is, there's a driving force. If this is 0, there's no driving force. And if this is less than 0, then we say if it's 0, it's at equilibrium. There's no driving force for net change. And if it's less than 0, there's a driving force in the reverse direction. Then reverse is spontaneous. So there are different ways of phrasing the second law. One way of phrasing the second law is that all spontaneous processes, all these processes that have a natural driving force, are going to be accompanied by an increase in the entropy of the universe. So there's processes that are happening all the time. And so this isn't like a zero-sum game like energy. Energy is like a zero-sum game, meaning that if somebody loses, somebody else must gain. In other words, there's a fixed amount of energy in the universe, essentially. And so whereas the entropy is constantly increasing. The entropy of the universe is constantly increasing. Eventually what's going to happen is the entropy is going to max out. When the entropy is maxed out, then everything's spread apart. In other words, everything's spread apart. There's no ordered systems, where things. Okay, so this is the second one. So we need to figure out how to calculate delta S of the system and how to calculate delta S of the surroundings. Delta S of the system is a bit easier. So let's take a look at that first. And what we're dealing with here is positional entropy. That's this. Delta H is going to deal with energy entropy. We want delta H calculations because we want energy entropy. Probably do this simply. As of exothermic, we're increasing energy entropy. And so let's look at positional entropy first. Qualitative is fairly straightforward. So if we have a solid, the atoms or molecules or ions are held together in a lattice, and this lattice is pretty well ordered. Everything should have its position, and so solids have low entropy, so S is small. Compared to liquids, there's a bit more disorder in liquids because we have translational motion. Also rotational and vibrational if the molecules are more complex. They're moving about. And then gases are going to have even higher entropies. So the greatest entropies we expect are for the gases. Those are going to have more disorder. Another way of thinking about this is constraint. Solid is much more constrained than a liquid, and a gas is the least constrained. The gas has the most, degrees of freedom. That's positional entropy. So what we want to do, though, is we want quantitative. We want actual numbers for these. And so in order to determine the change in entropy, or actually just the entropys themselves, we're often interested in the change, because we want to see if the entropy is increasing or the entropy is decreasing. So we'll need to know the final entropy and the initial entropy. But what's interesting about entropy, unlike internal energy and enthalpy, is that the absolute entropies, unlike absolute enthalpies and absolute internal energies, can be determined. Absolute enthalpies and absolute internal energies cannot be determined with any degree of precision. Does anybody remember why? Well, it has to do with the absolute zero, For entropies, there is an absolute zero of entropy, and that can be determined. However, with internal energy and enthalpy, it's hard to determine what exactly is our absolute zero point. Because the absolute internal energy, U, let's write it over here somewhere. U is equal to the sum of the kinetic energy plus the potential energy. Determining the kinetic energy is easy, and the absolute zero kinetic energy is zero when there's no motion. But what is the absolute zero potential energy? What has the lowest, can you tell me what has the lowest potential energy that you can think of? For in physics, it's not too bad. If we have a ball, up here, and we're looking at gravitational potential energy, where would the absolute zero of gravitational potential energy for this ball be? The ball would fall until it hits if it could. The ball would continue to fall until it hits the floor. Is that the absolute zero? How about bad water out in Death Valley? Bad water is 280 feet below sea level, I think. Is that the absolute zero, the lowest that ball can get? Well, probably in the US, unless there's a mine shaft, maybe there's a mine shaft you can drop the ball in, and then it hits the bottom of the mine shaft. Is that the absolute zero? The bottom of a deep mine shaft? Could it go even lower? How low can it go? If you could dig a hole all the way to China, would it go all the way to China and then stop? That would be the absolute zero of gravity? No, the absolute zero for gravity would be like the center of the Earth. If it hits the center of the Earth, then we can't go any lower than that, can we? Right? Center of the Earth. So potential energy, no problem. We can calculate the absolute potential energy, or we can calculate the relative potential energy, because if I drop a ball, it's not going to go to the center of the Earth. And so probably I'm more interested in the ball hitting the ground, And I'll call the ground what we call arbitrary zero or relative 0 point, It's like temperature. When we're thinking about temperature, you think, okay, 0 degrees C, is that rock bottom? Is that the coldest you're going to get, 0 degrees C? No, somebody just called that zero, just like they called sea level. They call sea level zero elevation. Anything higher than sea level is like, for example, Mount Whitney's 14,500 feet above sea level. We call that zero, but that's an arbitrary zero. But in order to determine the absolute internal energy, kinetic energy is no problem. Absolute zero kinetic energy is it stops moving. However, potential energy, what's the absolute zero potential energy? Tell me what object or what thing or what has a zero potential energy. I'm not talking about gravity. I'm talking about things like chemical potential energy, that we were discussing before. I told you that methane and oxygen have higher chemical potential energy than CO2 and water. CO2 and water has lower chemical potential energy. What has zero potential energy? Tell me. What has zero potential energy? Can you tell me? It's kind of hard because we just keep breaking things apart. So, you start taking things apart like a water molecule. A water molecule can be taken apart into 2 hydrogens and an oxygen. And then the oxygens can be taken apart into electrons, protons, and neutrons. And then the protons and neutrons can be taken apart into quarks, right? Up quarks, down quarks, these so quarks make up protons and neutrons. But can quarks be broken down further, or quarks the ultimate limit? Are quarks the absolute bottom? Well, anyway, fortunately, we don't have to figure it out. And so people don't figure it out. So whenever we have potential energy, this is just a relative scale. What they want to determine is the delta, the change in energy here. delta, that we can determine with great accuracy and precision. But the absolute ones we can't. Now, entropy is a little different. And so entropy is this. What is the absolute zero of entropy? What the absolute zero of entropy is the most ordered, most constrained thing you can think of. And so what is the most ordered, most constrained thing we can think of? So the absolute entropies can be determined. How to determine absolute entropies? One way is we can calculate it using the Boltzmann equation. The Boltzmann equation is the absolute entropy is equal to K, the Boltzmann constant. The Boltzmann constant is kind of interesting because Boltzmann constant is R, the gas constant, divided by Avogadro's number. And so it's R for a single particle rather than a mole. Ln, natural log of W. W is the number of ways things can be arranged. And so it's the number of, what did I say here, positions possible, number of microstates possible, number of ways you can arrange things. And so this brings us to the third law of thermodynamics. The third law of thermodynamics just states this. The entropy of a perfect crystal at 0 Kelvin is 0. And so if we have a perfect crystal, there's only one way of arranging the particles in a crystal. And at 0 Kelvin, there's no vibrations. The vibrations mean there are more arrangements. You know, if atoms are vibrating around, then they could be in this position or that position. You know, they're going to, depending on where in the vibrational cycle it is, it's going to give you a choice of positions. But if you freeze it down so that there's no atomic or molecular or ionic motion, then there's only one way of arranging this. So this is the third law of thermodynamics. So we can calculate it. So what we do is we try to figure out how many different ways of arranging things are there. So let's say if you have a quarter, you know, it could be heads or it could be tails. So if you have a quarter, that's kind of like two ways. It might be heads or it might be tails. We can calculate the entropy of that. If you have a dice, then how many ways of arranging that are there? Well, if you're just looking at, you know, how many dots come up, then would it be six ways of arranging that? If you have two dice, how many ways? Now it gets more complicated, right? Because if you have two dice, all of a sudden the number of ways of arranging it increase dramatically. Because you could roll two dice and get 1 and 1, or 1 and 2, or 1 and 3, or 1 and 4, or 1 and 5. Count all the ways. Can you count all the ways? If you have an Avogadro's number of dice, do you want to count them individually? If dice 1 is 1, then dice 2 might be 1, 2, 3, 4, 5, 6. Dice 3 might be 1, 2, 3, 4, 5, 6. Do you want to count all the ways? No. And so what people do is they don't want to count all the ways. They'll use statistics to figure it out, how many different ways of arranging it. And so this is why math could be very useful. Math could be very useful because it could save you a lot of time. You don't have to sit there and count it one by one. But it can get ridiculous, you know. This is why, like in physics, This is why in physics, typically they only look at the energy. They don't look at the entropy, because if you have a ball, how many ways are there of arranging a ball, Well, initially it's up here, so one way, and then finally it's down here, one way, And so the entropy is not going to be a huge factor. But in chemistry, you're looking at, if you have an Avogadro's number, then it becomes more complicated things in general. And so entropy becomes more and more significant. Usually the energy is the dominant term. We're looking at energy, minimizing energy. All right, so that's one. And so there's examples in the book about looking at how many ways of arranging things there are, which if you're interested in, I think I might have given a homework problem like this. Take a look at the calculation here. Okay, so Boltzmann view. We have these microstates. And then we can try to figure out how many microstates there are here. Oops. I'm trying to be careful with this since the other one, the connection's so bad, it doesn't work anymore. And so here in the ground state, there's only one way of doing this. And then they excite one of these balls up to that level there. But how many ways are there of this? So if we have one excited, it could have been the red one, or the brown one, or this one, that one, that one. And so it turns out there are 5. Etc. So this, once you do this statistically, then what we'll get, and this is a little bit more in-depth, it's not just a simple picture. What they're looking at is the electron in a box. And so we have this. This is actually engraved on his tombstone. The Boltzmann equation. The absolute entropy is equal to K. This is log base 10, I think. But whatever, we'll be doing the natural log. If there's only one way, the natural log of 1 is 0. And so the entropy comes out to be 0. That's Boltzmann. So if we figure out the number of microstates, we're all of a sudden, especially with, let's say, a mole of particles, the number of microstates is going to come out horrendous. Let's say they're 10 to the 23rd microstates. Just Avogadro's number of microstates. That's going to come out to this. Try punching this in your calculator. Do you think you're going to get a number? No. And so we're not going to be doing any Boltzmann calculations unless it's kind of for very, very small systems. But there are people who do work with this. They do statistical thermodynamics. And so they didn't give up, but we're going to give up. And then they're going to do it. So, and they can do it. It's not terrible. It's called statistical physics or statistical mechanics. They just figure it out. Okay. Is there another way of determining entropy, absolute? Yes, there is. And that's going to come through experimental measurements. Let's see. I can show you. This is the Clausius view here. But essentially this is ds. D just stands for, if you haven't had calculus, it's just a small delta, an infinitely small delta. And so this is delta S, the change in entropy. And this is delta Q, which is a very, very small change in Q, which is reversible over T. And so the change in entropy is related to Q reversible over T. And so I'm going to simplify this equation here to, oops, I guess that's how my last one died. Hopefully this one is not going to die as well. And so we're going to simplify this equation to this. In other words, delta S is equal to Q. This is the total heat at a given temperature. Now, this delta Q here, and this thing here is like just adding it up. This is called an integral. So we just integrate that. And basically it boils down to this here. Delta S is just going to equal Q reversible over T. And this is what we're going to get. Now, note that this is delta S. This is not S, absolute. This is a change in entropy. And the change in entropy is going to be related to the heat. Why is a change in entropy related to the heat? One of the reasons why is when we think about heat, you know, the amount of heat absorbed at a given temperature, we have a name for that. Do you guys recall the name? When we're looking at heat and temperature, what do we think of? This is back in chapter 7. Heat and temperature. What comes to mind? So, for example, water absorbs lots and lots of heat before its temperature rises, versus copper metal. Copper metal barely takes any heat and the temperature skyrockets. Yeah, the specific heat or the heat capacity, you know, they're all related. Specific heat, it just has units of joules per gram, degrees C. We also have molar heat capacity rather than per gram, per mole. And we have heat capacity of an object. So 3 heat capacities we covered in Chem 1A were specific heat, molar heat capacity, and heat capacity of an object like a brick or something that you don't want to weigh. Or what we call a bomb calorimeter. Do you want to weigh how many grams of the bomb calorimeter is? No. We just call it the heat capacity of an object. Well, if something has a high heat capacity, that means there are a lot of ways it can absorb heat. Well, what are the ways that things absorb heat? Well, things absorb heat by causing vibrations, rotations, translations. So water has a very high heat capacity because water can absorb lots of heat. What happens is it absorbs it and causes the waters to vibrate, rotate, and translate more. With copper metal, what can copper metal? Copper metal can only vibrate. That's it. And so water has lots of ways of absorbing heat. We call it a heat sink. It's an excellent thermal or heat sink. Whereas copper metal isn't that great of a heat sink because it can absorb heat rapidly, but it can't really store it. It has to dissipate it somewhere. It has to get rid of it. Usually it gets rid of it, you touch it and it's very hot. You get rid of it. And so that tells us, if there are lots of ways of absorbing this energy, that means there's lots of ways, microstates, right? Which means the entropy is higher for this type of stuff. So what we do for measuring this is we take heat capacity measurements. And so let me see if they talk about that here. No, they don't talk about it here. So basically, the experimental determination of absolute entropies comes like this. Okay, I thought this was already broken again. Delta S is S final minus S initial. And that's going to be equal to the integral. An integral, we just look. Integral is essentially taking the area under a curve. And then we're going to start at t equals 0 and then integrate over t, called t, of our q reversible over t. Here. If we always start at t equals 0, then this equation simplifies. So if we start at temperature equals 0, what happens at 0 Kelvin is we're going to form a perfect crystal. And so S0 goes to 0. And so this just becomes the absolute entropy. And so we can calculate the absolute entropy by integrating the area from 0 to temperature T. And what we integrate is this. We're going to integrate what we call over T. Although this is 1 over T, I'm going to plot this relative to T. And so if we start here, well, we can't measure it at 0 Kelvin, but we can measure it at temperatures close to 0 Kelvin. And so we measure the solid here, and it's going to have a fairly low heat capacity here. Then we can extrapolate this to 0. And then we go to the liquid. Liquids have the highest heat capacity, so it's going to jump up when it transitions to a liquid. So this is solid, this is a liquid. And then gases have lower heat capacities than liquids typically. And so this would be gas out here. And so let's say I want the entropy, absolute entropy at a given temperature. Let's say I want this temperature here. If I'm interested, this is my T final here. Then in order to determine the entropy, all I do is I measure the area, this is called integration, measure the area underneath the curve here. I just add it up. Add up the area here, and that gives me my entropy. for this. There to there. This we don't need to know. And then absolute entropies, what we do need to know is absolute entropies can be determined by heat capacity measurements at different temperatures. Can be determined by heat capacity measurements at different temperatures. Fortunately, somebody else has done all the work because calorimetry is not easy to carry out. And so if somebody else did all the work, then all we're going to do is just look at the data. So we're going to go to the thermodynamic data table, and here we're going to look at two more columns in the data table. We know our delta H's of formation. What does the F stand for? The F stands for, it's defined precise. What is the precise definition of F? It means, F means formation of 1 mole of substance from the elements in their standard format under the given conditions. And so the delta H of formation for this should be 0 because it's formation of aluminum, solid, 1 mole, from the element, aluminum, in its stable state under these conditions. What are the conditions for this thermodynamic table? Do you know the conditions? For this thermodynamic table? Well, the conditions, you have to read that. Thermodynamic properties of substances at 298.15 Kelvin. So it's room temperature. Substances are at 1 bar pressure. So 1 bar pressure and room temperature. For aqueous solutions, solutes are at unity activity, roughly 1 molar. Data for ions in aqueous solution are relative to values of 0. And so what the last sentence is saying there's an arbitrary 0 here for some of the data. And so you should know what these 4 sentences mean. Here, this is not an arbitrary 0. This is an absolute 0. I mean, this is 0 is fine because it's the reaction is aluminum solid goes to aluminum solid. There's no change in enthalpy. This is a review from chapter 7. You should review it too. As I can't spend too much time with this, so I'm going to leave this shortly. But this is not an arbitrary, or is it? This is formation of 1 mole of H plus aqueous from what? So delta H of formation of hydrogen ion aqueous. Does anybody remember this? In other words, Appendix D, they assume that you already know this. That's why they don't shoot. This thing is. What does this little superscript mean? Superscript 0. See, the problem why people fail thermodynamics, lots of people fail it because nobody remembers any of these definitions. Like all the basic stuff, people don't remember it, and then they get into the advanced stuff and they're just totally lost. They have no idea what that means. Rebecca, you remember? Not the heat capacity.
Is it initial?
Not the initial. This means this is under standard thermodynamic conditions. Okay, it's under standard thermodynamic conditions. Tell me what standard thermodynamic conditions are. Yeah, standard thermodynamic conditions are 1 bar, the new standard thermodynamic conditions, 1 bar, and well, the old standard thermodynamic conditions are 1 ATM. The new standard thermodynamic conditions are 1 bar. And the problem with thermodynamics, they don't review. They're not going to review anything. They're just going to jump into it and expect you to know it, you know.
25 degrees Celsius. Is it 25 degrees Celsius?
No. There's no standard thermodynamic temperature. STP there is, but there's no standard thermodynamic temperature. That throws people off too. It's just 1 bar and 1 molar, or 1 activity. Actually, unit activity, really. Supposed to be. But we'll just call it 1 molar. And so when I have the formation of H plus AQ, then this is under standard conditions. So it's going to be 1 molar. Do we always work with 1 molar H plus? No. No. So oftentimes we're working under non-standard conditions. If we work under non-standard conditions, can we use this data?
No.
If I'm working with 6 molar H plus, am I in trouble? Potentially. Yeah, because this data is for standard. And so you have to be careful with these things. Now, if this is a formation reaction, this is formation of 1 mole of H plus from the element. The element hydrogen, what's its stable state?
H3.
The stable state of hydrogen is H2. It's a diatomic element, and it's a gas under these conditions. And we have to balance this. This is going to be half a mole of hydrogen produces 1 mole. Now this is the definition here. This is going to be delta HF. And do you think this is equal to 0? No, it's not equal to 0, because first we have to break the hydrogen-hydrogen bond that's endothermic. And then we have to ionize it, actually. And then we have to dissolve it. And so breaking the hydrogen-hydrogen bond, ionizing it's endothermic, and then solvating it with water molecules is exothermic. And so delta H of F is not 0, but it's defined as 0. This is what we call an arbitrary 0. Why do we have this arbitrary 0? And I don't know if anybody remembers, but the example I used in Chem 1A, and I think most people use this one in Chem 1A. From Chem 1A, we were looking at delta H formation of 1 mole of HCl aqueous. Under standard conditions. Well, the delta H of formation under standard conditions with this is going to be 1/2 H2 gas plus 1/2 Cl2 gas is equal to HCl AQ. Now this can be measured or calculated using Hess's law, but delta H is minus 167 kilojoules. This is a very common example, so that's why I remember the number. And this is the example I use every semester in Chem 1A, so I remember the number. And so this minus 167 kilojoules, how much is it due to hydrogen? How much is due to chlorine? This is the problem. This is a problem where you have two unknowns and one equation. When you have two unknowns and one equation is, we don't know how much this is, so this is going to be x, and we don't know how much this is. This is going to be y. So is it 50-50? Is it 10-90? Is it 20-80? What percentage of this is due to hydrogen? What percentage of it is due to chlorine? So when we have two unknowns, obviously we want two equations, but sometimes we can't get two equations. In this case, it was impossible. Well, we could do some theoretical calculations to try to get to the second equation, but we don't, because the theoretical calculations are off a little bit. And so do you know what people do when there's two unknowns and only one equation? If we have two unknowns and only one equation, then I'm going to take the easy route out. I'm going to call x 0. If I call x 0, then y is minus 167. So x plus y equals minus 167. And so if x is defined as 0 and y is just y, then y is minus 167. But you're going, well, that's ridiculous. It's not 0% hydrogen, 100% chlorine, right? That's going to lead to an error. Yes, it's going to lead to an error. But you have to keep in mind, is it possible to have reduction without oxidation? No, you have to have reduction and oxidation, right? Together, you can't have one. So you can't have reduction. You can't have oxidation. It has to be reduction and oxidation, right? Can you form a cation without forming an anion? No. Here, we're taking the elements. We've got to form one cation, we've got to form one anion. The cation is H plus, the anion is Cl minus. And so what this means is this. Hopefully it makes more sense than last semester. Last semester I tried to explain this like 3 times, I think. But what it means is this. It means that since we can't form one without the other, then all the cations are going to be reading off one direction, and all the anions are going to be reading off in the opposite direction. So that when you combine them, the systematic error cancels. So do you see the cations are going to be off one direction and the anions are going to be off in the opposite direction, right? And then the error cancels. So if I take x plus y, I get the correct answer, minus 167. Can you see that? So this is what I mentioned last semester. I mentioned last semester that Appendix D is actually 3 tables in one. And they don't tell you it's 3 tables in one because they expect you to know that already. And this is the problem with thermodynamics. If thermodynamics gave you a little review each time you did it, then it would probably be, the pass rate would probably be higher. But anyway, we cannot compare. So when you're looking at cation, never compare cation with a neutral compound. So this minus 75.9 is like reading the Celsius scale, and this 3091.5 is like reading the Kelvin scale. So do you have a table in which you're going to see Celsius and Kelvin temperatures all mixed up with no units on them? No, but this is a table like that, you know. And so you have to know this, that you can't compare cations with neutral, and you cannot compare cations with anions. You compare cations with cations, anions with anions, and neutrals with neutrals. Then when you take a cation value and an anion value, then the cation's off one direction, the anion's off another direction, and they systematically cancel each other out, so you get the correct answer when you add them by Hess's law. All right, the same thing applies for absolute entropies. here. Take a look at the absolute entropy of H plus. The absolute entropy is this third column here. Is a 1 molar H plus solution at 298 Kelvin room temperature have 0 entropy? Is that possible? No way, that's a huge error, isn't it? Because H plus, this got translational motion, it's moving about, the water molecule's all moving. There's so many different ways of arranging an H plus ion in that 1 mole, 1 molar, that is 1 liter of liquid. And so this is what we call an arbitrary zero. This is an arbitrary zero as well. These are arbitrary zeros. And so you have to know that here. Obviously, H plus has a positive entropy. You know, let me ask you, what's greater, the entropy of hydrogen gas or the entropy of H plus molar? I ask this question all the time on the test. Or similar questions like this. Which one has a higher entropy, H plus AQ or hydrogen gas? And which one would have the higher entropy? The hydrogen gas. Yeah, well, obviously it's got a higher entropy. It's 130, right? Okay, but let me ask you this. I'm going to ask you, which one has a higher entropy? Aluminum solid or aluminum 3 plus aqueous? Which one has a higher entropy? Aluminum solid or aluminum 3 plus aqueous? Which one has a higher entropy? Aluminum 3 plus aqueous. Why? That's correct. And a lot of people will go, no, it doesn't. It's minus 321.7. Well, minus 321.7, is that a violation of the third law of thermodynamics? What does the third law of thermodynamics state? Third law of thermodynamics states that the absolute zero of entropy is a perfect, because there's only one way of arranging a perfect crystal at 0 Kelvin, right? Does that mean there's fewer than one way? There must be a negative number of ways of arranging aluminum 3 plus ions in 1 liter of solution. Is that correct? Or what's going on here? What's going on here is you can't compare. You can't compare Fahrenheit with Kelvin, can you? This is like Fahrenheit, that's like Kelvin. What's absolute zero in Fahrenheit? Minus 450, minus 454, right? Fahrenheit is minus 454. And so in other words, just reminding you about the table. You know, this should have been clear in Chem 1A, but if it wasn't, then we're going to see it again, and we're going to see it again. But there are like 3 tables in one: Fahrenheit, Celsius, and Kelvin. So be aware of that. So anyway, getting back to this, and then we have, what is this called? CP. This is called the molar heat capacity at constant pressure. So that's CP. So we have the heat capacities there. Those are going to be related to the entropies. I don't know why they put this in here, because we really don't do much with it. Okay, so how much time do we have left? 15 minutes? 20 minutes? Yeah, 20 minutes. So just go back and take a look at chapter 7 and try to review some stuff from chapter 7, because this is going to be it, I think, for review, unless there are questions. If you have questions, then I'll review whatever. But I'm going to stop reviewing chapter 7 and then just get into chapter 13 directly. But the first thing we want to do is we want to look at the entropies. And so take a look at the entropys of solids. 28. This, the solids have, when we look at the table, and you should do this, the solids range from entropies from about 0 to 100. When we see solids that have entropies greater than 100, that's kind of high, like aluminum chloride here, greater than 100. This is typical here. This is quite high, aluminum sulfate, 239. You know, that's getting into liquid territory. The reason for aluminum sulfate having such a high entropy is the sulfate has rotational motion within the crystal lattice, and so they can rotate. So it gives a lot more positions that we can have. Then we look at the liquids. The liquids are around, 100 to 200. The units here are joules per mole Kelvin. And then gases are going to be over 200. Some gases are a little higher than others. You know, gases with more complex molecules are going to be a little higher. Like B2H6, there are going to be lots of vibrations, vibrational modes. It's a bit higher. BF3 is even higher there. Why is that? Well, it can be because there's maybe more order, less order. So we're looking at gases being, this is a very simple gas. This is just a monatomic gas, 175. This is on the low side for gases. And so liquids about 100 to 200, gases above 200. And then we have, some spread depending on if it's a well-ordered liquid. Some liquids are quite well-ordered. Let's take a look at water as an example here and see if that's fairly well-ordered. H2O. I think it's under oxygen. No. H2O. Yeah. Take a look at H2O liquid. Wow. 69.91. It's pretty low. It's kind of in the solid territory. And so this has got strong hydrogen bonding interactions, which holds the water molecules in certain positions. It limits the mobility or the freedom of the water molecules. Okay, I'm going to stop